So when we are selecting an image compression technique, we have to make sure that for what purpose we need that image compression techniques. Mostly if you want to use the image, the digital image for designing an application, it's better to go for lossless compression. The file formats that are supporting the lossless compressions are the TIFF file format, TIFF or TIF, or the PNG file format, the PNM file format. But if you need the image for uploading over the internet, in constructing web pages, it's better to go for LUSI. And for that, JPG, JPEG, GIF for animated ones are there. So accordingly, we have to do. But in any case, image compression is critical. So by using the image compression techniques, as said earlier, we can save more memory space. Accordingly, we can keep more data, image data. But we have to make sure that the content, the quality, the naturalness of the image is kept as it is. Especially it has to not noticed by the sense organs of the human being. Our eye should visualize the same thing always. Our ear has to hear the same audio always. So whenever we choose any of the LUSI or lossless compression techniques, we have to make sure that there is no quality or naturalness effect on whatever data that we are producing. So especially for spreadsheet, textual document, executable files, we can go for lossless but not LUSI. Text compression can always be done on using lossless. Executable files should be always compressed using lossless. But when it comes to multimedia, image, audio, video, it's possible to go for either lossless or LUSI. By simulating the human sense organs, we can use lossless and the LUSI compression techniques for saving as much memory space. We can transmit as much data over the limited transmission bandwidth. So when we are looking at compression techniques, nowadays they are classified into two. Static coding means statistical methods, and adaptive coding, which is a dictionary-based method. The major difference between the two is static coding means we are trying to compress a static data, like textual data, image data, are static by their nature. So for that, we need static coding. But at the same time nowadays, there are animated, time-dependent data we have. Audios, videos, animated images are time-dependent. For time-independent, we can use static coding. But for time-dependent, we need another algorithm, because in a time-dependent, the full content is not available as it is at one time. It comes through time. So as the data is appearing, we have to capture it and we have to compress it. For that, we need adaptive coding. So static codings are a two-step approach. They are using statistical information in behind during compression. Given textual data or an image data, the first step for static coding is collecting information about the probability of appearance of every symbol. For textual data, the probability of occurrence of every characters or every words. For image, it has to capture the probability of occurrence of every pixels. Then after gathering the information, compression will be done using like Hoffman coding, entropy coding. But when we come to adaptive coding, since the full information is not available, there is no way to calculate the probability of occurrence of symbols within an image or within a textual data or within an audio file. So the data should be compressed while it is appearing in our output devices. For that, adaptive codings are following just one step. While the data is appearing without any statistical information, it has to compress immediately. For that, there are algorithms like Lemper-Zip or adaptive Eban-Hoffman coding. If you see Hoffman coding, the name is given by the author of, the creator of the Hoffman algorithm, David Hoffman. It's created long years back, and it is nowadays widely used for textual compression, like zip softwares, RAR softwares are using it. Even multimedia codecs are using Hoffman coding. Whenever we transmit message like over the fax machine, also they are using Hoffman coding. The major principle in Hoffman coding is creating a Hoffman tree. The tree is binary. Why binary? Because the tree is designed based on binary bits, zeros and ones, since we are dealing with a digital image and every pixels are represented by binary. So finally, when it is trying to construct the Hoffman tree, it's constructing using two branches at every point. Given whatever textual data or image data, the Hoffman tree starts from a given root node, then it goes on until it reaches to the leaf node, and the leaf nodes are telling us the symbols lying over that path, starting from the root. So if you go starting from the root node, then until you reach to the given symbol, the bits are assigned for the branch. So every edges are containing one bit, either 0 or 1. If you are assigning 0 for left branch, the right branch is assigned 1. Whether you are applying Hoffman coding or any other coding like entropy, we have to make sure that we are using consistently the same binary bit assignment. If the left branch is assigned 0, the right branch should assign 1, or else if the left branch is assigned 1, the right branch should be assigned 0. So one convention we have to follow says that whatever we compress is possible to be decompressed. So the major thing for Hoffman encoding is, since it is a static coding or statistical encoding algorithm, given textual data or image data, it's trying to calculate the probability of occurrence of every symbol in that textual data or image data. How can we calculate probabilities? The probability is calculated by taking the frequency of occurrence of a given symbol over the total number of symbols in that given textual data or image data. So that will give us the probability of occurrence of every symbol. Once we calculate the probability of occurrence of every symbol in that given image or textual data that we want to compress, then we can follow the Hoffman encoding algorithm. The Hoffman encoding algorithm, for every distinct symbol, it's creating a forest of trees by assigning every symbol, by initializing every symbol as one tree. Finally, based on the number of symbols that we have, if there are n symbols, we have n trees in our forest. That's why it's called also forest of trees. That means there are multiple trees. But Hoffman encoding is trying to bring those forest of trees into one tree. So until one tree is constructed, it starts merging the trees. But to merge the trees, the first step is we have to sort the trees as per their frequency of occurrence in increasing or ascending order, or in non-descending order, or non-decreasing order. Once we sort, then we have to take the two trees with the least probability. Merging in a tree means what? Merging in a tree means connecting those trees with one root node. And the root node is assigned with the sum of frequency of every tree. If tree 1 is with a frequency of 5, and the tree 2 is with a frequency of 9, when we are merging the two, the tree is containing two trees with frequency of 14. So the root node is assigned 14, which is the sum of the probability of occurrence of T1 and T2. Then once we connect two trees, then we have to have the convention either the left branch should be assigned 0, the right branch should be assigned 1, or the left branch should be assigned 1 and the right branch should be assigned 0. In our case, we will follow left branch assigned 0, right branch assigned 1. Finally, it is running again and again until the forests of trees are reduced to one tree. But every time sorting is required. Why we are sorting? To order our trees in increasing order, starting from the least frequent one to highly frequent one. Then after sorting them in ascending order, we have to pick the first two with least probability. Then we have to merge them by connecting them through creating a root node, which is assigned the sum of the frequency of or the probability of the two trees that we are merging. Finally, we have to label the branches with 0 and 1. If left branch is assigned 0, the right branch should be assigned 1. So the while loop is exiting when Hoffman encoding algorithm reaches to only one tree. When when the system is exiting from the while loop, then we have to start creating a unique code word for each symbol. When we are creating a unique code for each symbol, we have to traverse starting from the root, following the path until we reach to the leaf node where we are getting a given symbol. All the bits that are available at every branches should be concatenated starting from the root node until we reach to the leaf node. That will give us a bit representation for every symbols. In this example, already the probabilities of the symbols are calculated. A is occurring 0.05 times, B is occurring 0.05 times, C is occurring 0.1 times, D is occurring 0.2, and so on. So from that textual data, we obtained 7 symbols with their probabilities. Now we want to construct the Hoffman tree using the Hoffman algorithm. So the first thing is we have to create forest of trees. After creating the forest of trees, that means A is one tree, B is another tree, C is the third tree. Accordingly, we have 7 trees. Then we have to sort them based on their probability in increasing order. If you sort them in increasing order, A comes first. Of course, A and the B has equal probability. But then if 2 or more symbols have equal probability, we can go for ordering them alphabetically. So we have to follow some convention consistently. In our case, we can follow alphabetic order. So A comes first, followed by B, then C, then again 0, 1, G. So A comes first, followed by B, then C, then G, then D, again 0.2 F, finally E. So when Hoffman encoding works, since there are a tree with 7 trees, forest of trees, so the while loop should start merging 2 trees. To merge 2 trees, we have to select the 2 trees with least probability. That means from left to right we can go. So which 2 symbols we are merging? Since A and B are the least frequent one, we can merge A and B. When we are merging A and B, means connecting them by creating root node. A is 0.05 frequency. A is appearing with probability of 0.05. B is appearing with probability of 0.05. The sum of the probability of A and B gives us 0.1. That means the root node is assigned with 0.1. After merging A and B, the size of the forest of trees is reduced by 1. Originally, we have 7 trees in our forest, but now after merging, we have 6 trees in our forest. So then after merging again, we have to sort. Since C and the G are with 0.1 probability, and now the merged tree has 0.1 probability. So the merged tree comes first, followed by CG and others. Again, we have to connect now or merge the tree with 0.1 probability with the next tree, least probability containing C. When we are merging a tree with 0.1 with C, again we have to merge them by connecting them through root and assign that root node with 0.1 plus the probability of occurrence of C, 0.1. 0.1 plus 0.1 is 0.2. Now we merge it, a tree containing AB with a tree containing C with a root node of 0.2. Since there are 3 symbols, the 3 symbols are occurring 0.2 times. Again, after merging ABC, we have to sort them. Which one comes first? Since the merged tree is with 0.2 probability, G is with 0.1 probability, so then G comes first, followed by 0.2. D and F are with 0.2 probability, then finally E with 0.3. So now we can merge G with 0.2. Now G appears in the left side, and the tree with 0.2 frequency appears on the right side of the root that we are creating. When we connect G with a tree with 0.2 probability, which contains ABC, we are creating a root and assign the root with probability of occurrence of G and ABC. That means ABC are occurring 0.2, G is occurring 0.1, 0 plus 0.2 is 0.3. Every time, don't forget, the branches are assigned 0 and 1. In our case, the left branch is assigned 0, the right branch is assigned 1. At every point, we are assigning the left branch 0, the right branch 1. Now also after merging G with ABC, we are assigning the left branch 0 and the right branch with 1. Now our forest of trees are reduced by 1. Then when we are sorting them after merging, D and F are coming first, followed by 0.3 and E. Because D and F are with 0.2 probability. But the one which is merged and containing ABC has 0.3 probability, finally E. So now the two trees that we are merging is the D and F with least probability as compared to a tree containing ABC and E. When we are merging D and F, we are creating a root node with the sum of probability of D and F. D is 0.2 and F is 0.2, the total is 0.4. After creating a tree for D and F, again we have to sort them. After sorting, 0.3 comes first, followed by E also 0.3. Finally, the current merged tree containing D and F comes last because the frequency is 0.4. Now when we are merging a tree with 0.3 frequency and E, the tree with 0.3 comes to the left of the root node and E comes to the right of the root node. And the root node is labeled with 0.3 plus the frequency of occurrence of E 0.3, the total is 0.6. Again, the left branch is assigned 0, the right branch is assigned 1. Finally, we have now two trees in our forest. The one with 0.4 root node and the other is 0.6 root node. When we are merging the two, the root node is assigned with 1. Obviously, at the end of the day, the probability of occurrence of the total number of symbols in our collection gives us 1. So in the meantime, we will also check the correctness of our Hoffman tree if finally we get 1. So now the left tree is with the one with 0.4. On the right of the root node comes the one with 0.6. Now we have only one tree. So then the while loop will also exit, since we have no forest of trees. If the while loop is exiting, the next step is generating the code word for every symbol, A, B, C, D, E, F, G, because we have 7 symbols. So based on the tree constructed, we have to also generate the code word for every symbols, starting from the root node, following the path until we reach to the given symbol. How much code word do we have to assign for A? A is at this point. Starting from the root node, if you traverse the tree until you reach to symbol A, you will get the binary bits that are used for representing symbol A, B, C, D, E, F, G. So starting from the leftmost symbol, we can go until we reach to the rightmost path in that given tree. So you will get D. D is lying on 0, 0 path. So D is assigned 0, 0. What about F? F is assigned 0, 1. So this 0, 1 and the 0, 0s are used as a representation for those symbols during compression. And this code word is important. If you are using it for compression, you have to also use it for decompression. Nowadays, zip file by itself is also saving the code words of every symbol as a model, as a reference point for compression and the decompression of the textual data. Once we generate the code word for every symbol, then we can compress whatever words or statements given. For instance, I want to compress CAFE, cafe. What is the code word that we have to assign for cafe? If you are using ASCII, since every symbols are assigned 8-bit, for the 4 symbols, 4 times 8, we are assigning 32 bits. But if you follow Huffman compression techniques, C is assigned not 8-bit. C is assigned 1011, only 4-bit. What about A? A is assigned 1, 2, 3, 4, 5 bits. What about F? F is assigned 2 bits, 0, 1. What about E? E is assigned 2 bits, 1, 1. So the total bits that we are assigning after compression is 1011, 10100, 0111. That means the total compression from 8 times 4 to 4, 8, 12, 13 bits. So 32 bits is reduced to 13 bits. And the degree of compression is 32 minus 13 over 32. But since Huffman coding is keeping the code word are long, the compressed data, that the model, the code word by itself is taking memory. So our compression is not that much more than 15%. You can exercise on the word Mississippi. Mississippi contains around 11 characters. But if you see the distinct characters, there are only 4 distinct characters. Since M is occurring 1 time, I is occurring 4 times, S is occurring 4 times, P is occurring 2 times, using the frequency of occurrence of every symbol, we can apply Huffman compression for compressing the data in the C. To what extent? The data is compressed to save memory space. The other algorithm that is used for static coding is entropy encoding. We know entropy is in information theory a measure of the content of the information available. It can measure the degree of disorder happening in a given data. And the information content can easily be defined. One is containing information, 0 is not containing information. That can be calculated by using the probability of occurrence of a given symbol multiplied with logarithm of the probability of occurrence of that symbol to the base 2. Given a grayscale image, in a grayscale image, as we said, there are 256 colors. And if every color have equal chance to be represented, to appear in a given grayscale image, the probability of occurrence of every grayscale color is 1/256. What is the probability, or what is the entropy? The probability of the probability of occurrence of every grayscale color is 1/256, and the entropy of a grayscale image is summation of all the colors that are available by taking every color and multiplying 1/256 of that given color multiplied by the logarithm of 1/256, 1 over the probability of occurrence of that color to the base 2. Why base 2? Because we are using binary. 2 bits. 1 over 256 times logarithm of 1 over 1 over 256 to the base 2. 1 over 1 over 256 means logarithm of 256 to the base 2. Since we are summing over 256 colors, we are summing over 1 over 256 times the logarithm 256 times. So this 256 cancelled by the 256 times that we are multiplying every colors by 1 over 256. So finally, we are only calculating the logarithm of 1 over 1 over 256 to the base 2. So 1 over 1 over 256 means 256. Then logarithm of 256 to the base 2 means 256 is to the power of 8. 2 cancels 2. Then we have 8 bits. That means the information content of a grayscale image is with 8-bit entropy. That's why 8 bits are used for grayscale image. Since there are 256 colors, every colors are requiring 8 bits for representation. What if the image is a monochrome image? We have only 2 colors, and the probability of occurrence of every color is 1 over 2. And if you calculate, you will get 1 bit as an information content and entropy. Then if you calculate entropy of a source image with m symbols, if every symbol are equally likely to happen in that given image, what is the entropy? If there are m pixels in an image, and if every m pixels are equally likely to happen in that given image, the probability of occurrence of every pixel is 1 over m. So then, rather than using summation of 1 over probability of occurrence of every symbol multiplied by logarithm of 1 over probability of occurrence of every symbol to the base 2, we can only use logarithm. So if a given image has m pixels, and if every pixels are equally likely to happen in that image, the probability of every pixel is 1 over m. Logarithm of 1 over m to the base 2 is 1 over m is m. So finally, you will get logarithm of m to the base 2. This is the entropy. Basically, logarithm of 1 over the probability of occurrence of a given symbol to the base 2 will give you the information content available with a given symbol. So from this, we can understand that entropy can tell us a threshold up to what point we can compress a given image or text or any multimedia data. Multimedia data is containing text, image, video, and audio. When you are calculating entropy of a given data type, you are getting the minimum information content available in that given data type. So we can use it as a benchmark for designing an algorithm. For instance, if the probability of occurrence of character E in this slide is 1 over 16, what is the information content of symbol E? Logarithm of 1 over 16 to the base 2. That means logarithm of 1 over 16 to the base 2 is logarithm of 16 to the base 2. 16 means 2 to the power of 4. Logarithm of 2 to the power of 4 to the base 2 is 4 bit. So every symbol E appearing in a given content has 4 bit. And then if there are around 5 is appearing in that given content, 5 times 4 is 20 bits. Information content of E is available. So we can go up to 4 bits to compress character E. For that one of...
Hello, Doctor. Hello.
አቤት
ሁለት ደቂቃ አካባቢ ነው ይቀራልና እንመለሳለን ወይስ እንዴት ነው የሚሆነው?
አሁን እንኳን የሌላ ክላስ አላችሁ አይደል? ይሄንኑ እንደምን
ሌላ ክላስ አለ። ሰዓት ግን ትንሽ ቢሻሻልን ዶክተር ያነሰችብን ነውና
ሌላኛው ክላስ አላችሁ ብዬ ነው።
ወይ ሌላ ቀን
ላይ እናመጣዋለን። ቆይ እንነጋገርና ከሪፕሬዘንታቲቮቹ ጋር
እሺ
ወደ ላይ የምናመጣበት መንገድ ይፈልግ።
እሺ thank you.
One of the algorithm designed to apply entropy coding is the Shannon-Fanon encoding algorithm, which is trying to simulate by using as a benchmark the entropy information content. So Shannon-Fanon, like Hoffman, it's also trying to compress, but it follows static coding. Like it first calculate the frequency of occurrence of every symbol. After calculating the frequency of occurrence of every symbol, it is trying to sort the symbols in not in increasing order like Hoffman. It is sorting in decreasing order, starting from the most frequently occurring symbol to the least frequent one. Then until each symbols are appearing at the leaf node, it is trying to, in previous case, in Hoffman, we are trying to merge. But in this case, we are trying to split. Because all the symbols are appearing within the root. And every time we are splitting them into two. When we are splitting them into two, we have to make sure that which appears to the left side and to the right side should have near to each other frequency.